So I'm interested in the yellow ball now, and what I'm doing is I am putting the projectile launcher, which you'll see in just a moment, on top of a table, my saw table of all things, and it is 1.18 meters tall. And I'm going to launch it, and since we calculated how fast the yellow ball is going to be moving, we said 6.1 meters per second. I'm going to launch it horizontally from the top of the saw table, and I'm going to predict where it's going to land. And I'm going to measure and see how close I am to that prediction, and I'm hoping to film the whole thing so that you can be a part of this too. All right, so let's predict the landing point of this projectile. All right, well, let's figure out how long it's going to take to land. So to find the time, I'm going to use the equation. Let's see, y final equals y initial plus v initial t minus 1/2 gt squared. And I'm going to plug in what I know is 0. And y final is 0 because it's going to hit the ground. Y initial is going to be the 1.18 meters, which I'll substitute in a minute. V initial. Now, even though it's moving at 6.1 meters per second, that's its V initial in the x direction. So this is where I have to break up what's going on in the x direction in the y direction. We haven't done this before for kinematics. We've always just looked at the x direction or the y direction independently. But here I'm interested in what's going on in y separately from what's going on in x. So even though it's being launched at 6.1 meters per second, that's in the x direction. In the y direction, it's just like it's being dropped. So that's what we have to use for this v initial y to determine how long it's going to take to hit the ground. This is 0 because it's the y direction. That's easily mistaken on problems involving projectiles, so be aware of that, please. And g, of course, I will use 10 meters per second squared right now. I'll just stay consistent with that, even though 9.8 is probably a little bit more accurate. So I'm going to say 0 is equal to 1.18 meters minus 1/2 of g is 5 t squared. So I'll say 1.18 meters equals 5t squared. Solve for t. T squared equals 1.18 meters divided by 5 meters per second squared. The meters are going to cancel, and I'm going to be doing a little bit of math here, but I'll have to take the square root of 1.18 divided by 5, and that's going to be seconds. That's going to be how long it should take my object to land. All right, so we calculated that it's going to take the square root of 1.18 divided by 5, or 0.49 seconds, for the ball to hit. This is the yellow ball. And since the initial launch velocity, so now I'm going to look at the x direction. So we just looked at the y direction. That told us how long it's going to take to hit. The x direction is going to tell us how far until it hits. How far will it go? So the kinematics equation for x position is this. X final equals x initial plus v initial times time. I'm going to put a little x there so you know that's the initial x velocity. Plus 1/2 at squared. Now you might ask, why am I using a and not g? The reason is because this isn't free fall. This is the x velocity description here. And you might also ask, what is the acceleration in the x direction? Well, we're going to ignore air resistance here. And if you ignore air resistance, I'm going to ask you the question, is there anything that's going to change the x velocity? Yes, the y velocity is going to increase that way because it's going to be accelerating. The x velocity should remain the same. So the acceleration should be 0 in the x direction. The initial x velocity, that's our 6.1 meters per second. The time, that's the 0.49 seconds. I rounded it to 0.49. And the initial x position I'm going to take to be 0 meters. So my final x position after all this is simply just the initial x velocity times time. What could be easier than that? That's all we need to know for the projectile to figure out where it's going to land. Once we know how long it's going to take to hit the ground, we multiply that by the initial x velocity, which is the average x velocity because it doesn't change. That should give us how far the object moves when it hits. On the little figure here, x final will be this distance here. All right, so if I plug things in here, I have the initial x, I have 6.1 meters per second. Multiply that times 0.49 seconds. And I did that, and I get about 2.96 meters. Now we're going to try it and see if that's what we get. Is that where the object is going to land, at 2.96 meters in front of the launch point? All right, this is a projectile launcher, and it will allow me to launch this little yellow ball, and I know where the ball should land, so I put a blue X on my garage floor. And I'm going to see how closely I can see where the ball lands relative to the little X. And of course, it's difficult to video it clearly so you can see exactly where the ball lands because of the timing of the camera and all that. But I did the best I can, so the next little segment will show you that. And what you'll see is that the ball lands pretty close to the little blue X, maybe a little bit past it, reflecting a little bit of inaccuracy associated with measurement of angle, probably the measurement of the initial velocity of the ball, and maybe the measurement of the height of the projectile launcher. So little things like that contribute to the error, but you can see that it's fairly close. So with projectiles, we should be able to predict pretty accurately where the ball is going to land. Okay,